we should be okay. We can do these two examples, but I'm not going to ask you to do this on the test. Okay? I will not ask you to do this on the test. This is the very next thing after the ones we just looked at. Okay? So don't worry about filling in that one or that one. I think we might have done it. I might have showed it to you on the PowerPoint, but I'm not worried about you focusing on this. Don't worry about this. I'm not going to ask you to do it on the test, and I'm not going to see it on the final. So we'll skip that one. So this is where we left off last time. We did this example. And I asked you to go ahead and look at the rest of the examples in preparation for today. So if you did what I asked you to do, you should have those in front of you right now. Let's go through and work these and make sure that you know how to work them. And I'm going to ask some of you to give me different answers to things. So I'm going to go through the problem and underline some things and ask you to tell me, what did that tell us? What piece of information did that give us? Because that's the important part of being able to set these up. First sentence says, and actually I think we've already done this one too, didn't we? Yeah, we did this one. So just to get you warmed back up again, simple random sample of 40 recorded speeds in miles per hour. What is that? What did that tell us that we're going to need to know? Your value of n. That's obtained from cars traveling on a section of Highway 105 in Los Angeles. The sample has a mean of 68.4 miles per hour. Somebody else, what did that tell us? What piece of information did that give us? It gave you X bar. And that sample has a standard deviation. And the symbol for that is?
No, you put the standard deviation, you meant 68.4.
Oh, sorry. Thank you. So then the 5.7 is S.
And now you know that it's going to be an X. Or
And that's right. That's very good. As soon as you know that, because you have a mean, but you don't have sigma, you know that this is going to be a t-test. So you've already picked out a very important piece of information. Okay? Is the mean speed of all cars traveling on Highway 105 greater than the posted speed limit of 65 miles per hour? What does that give us? That gives us a value for mu. And what does it get? It says mu is 65 miles per hour, doesn't it? Because that's the posted speed limit. Okay? Last part. Use a 5% significance level. What did that tell us? Exactly. Thank you, Zach. Now, we have not yet started the hypothesis test. We were gathering information. Okay? We're just gathering the information. Now that we've gathered it, step one. Tell me the claim. That's right. This tells me the greater than because it always goes with mu. If that's not true, what is true? Okay. So now that we know that, which one of those is HO and which one of those is H1? Is this HO or H1? That's HO. In fact, as soon as they tell you this, you're going to know that's HO. Because it said it was equal to. That was the posted speed limit. That means that the only alternative we have then is that's H1. So H1 in this case is the claim. Okay? It's not always the claim, but in this case it was the claim. So now we need to conduct the test. We know it's going to be a t-test. First thing it says is, do you have data or statistics? Which do we have? We have stats. Second question is, what is mu sub 0? 65. Then it asks about the sample. X bar, S, and N. X bar is 68.4. S is 5.7. N is 40. Then we need to let H1 do its job. What does H1 say about mu? Not equal to, less than, or greater than. It says greater than. You choose greater than. And then the last choice is calculator draw. we're going to draw because the picture actually helps us understand the answer. Okay? Now the calculator didn't tell us this, but remember HO's job is to tell you the center of the curve. And H1's job is to tell you that your test statistic and your p-value need to be in that end. And notice that it didn't shade anything in. There's nothing shaded. Okay? But it does tell you that the test statistic is 3.7725. And I'm sorry, I put that in the wrong end. Because it said greater than, I marked the other side. So it does go to the right side. So your test statistic is 3.7725. Now I want you to think about this for a minute. If you had a value from a random sample that fell 3.7725 standard deviations away from the middle, and you know from the empirical rule way back in chapter 6 that all of your data, all of your means, for all intents and purposes, should have fallen within 3 standard deviations. What does that tell you about your sample? Your sample mean is a lot higher than it should have been. It shouldn't have happened just by chance. And yet it happened. So because we know that this means that this sample is very unlikely to have come from a population that was following the speed limit, and also because the p-value, and this is, I'm telling you this partly so you'll realize why that p-value is so small. Your p-value is 0.0003, very nearly 0. Then it is not likely those 40 cars were observing the speed limit. They were speeding, okay? So while HO says the speed limit's 65 miles an hour, and that means the traffic on average was supposed to be going 65 miles an hour, we have a p-value that we're going to have to say is less than alpha. You reject HO. And when you reject HO, you say there is sufficient evidence to to show that the average speed is greater than 65 miles an hour. And I wrote down, you know, the kind of common sense conclusion, the cars are speeding. That's not strictly true. The cars aren't speeding, the drivers are speeding. Cars can't speed if the driver doesn't give it gas. Okay?
So, and that, would we ever say, like, since we reject the whole, that means that it's insufficient, or you just say, if there is sufficient evidence, you don't have to say anything about rejecting the
No, your actual, you'll always want to tell me I reject HO, so I'll know that was what you did.
Okay.
But then when I ask you to write me the conclusion, you don't reference HO. You say the evidence supports that the drivers on Highway 105 or whatever it was were speeding,
Okay.
or they were driving faster than 65 miles an hour. Okay? I mean, there's not a one single right way to say it. Different people use different words, but it has to have that same meaning. It has to have the same intent. Okay? Okay, a few more for practice. Simple random sample of the weights of 19 green M&Ms has a mean of 86 or 0.8635 grams. That gave us two pieces of information. What did it tell us? Okay, the sample size was 19. And it told us that 0.8635 was what? X bar. Then we get an assumption. It says, assume that the standard deviation of all green M&Ms is 0.0565 grams. What is 0.0565 grams? This is the deviation. It says it's standard deviation. Which one is it? It's the population because it says of all. Okay?
So that should be a Z-test, not a T-test.
That's right. That's a Z-test.
Why is it
Because it says the standard deviation of all green M&Ms. Every one of them, not just your sample, but every one of them. Now, if you're wondering how would they know that? Well, they would know that based upon the fact that there's a machine makes M&Ms. It measures out little amounts of chocolate into those little molds and molds it into little round pieces of chocolate candy, and then it runs through another machine that drops those little round pieces of candy into that hard shell candy coating and takes them back out and lets them drain. Okay? And those machines are set to only use a certain amount of chocolate, and they're set to use only a certain amount of that candy coating. Now, while they might get out of calibration, which means the mean might change a little bit, the standard deviation, if the machine is calibrated and left calibrated and it doesn't get out of adjustment, that machine is supposed to keep that same variability among all of them. It's supposed to stay within a certain margin of error on the amount that it puts in. So they could make a good inference about the standard deviation of the weights of M&Ms. But this fact that there's sigma and the fact that it's about X bar and the fact that you do have sigma tells us right now, before we go any further, this is going to be a z-test. Because it's a test about a mean, because they gave us a sample mean, and they gave us a sample standard deviation. So we know this is going to be a z-test. And then it says use a 0.05 level of significance. So that told us alpha. And then here comes the claim. There's your claim. Says the mean weight of all, so that's mu, green M&Ms is equal to 0.8535. Okay? What is the opposite of that claim? Not equal to. Which one's HO, which one's H1? Okay, top is equal, so that's HO. Bottom is not equal, so that's H1. This is going to tell us the center of the curve. This is how we're going to perform the test and decide what tail the test statistics in. So eventually, we're going to get a curve when we run the test. And the assumption of HO says the middle of that curve, we believe, is supposed to be 0.8535. But H1 tells us, because it says not equal to, it tells us that it is a two-tail test. So if we fall down here or up here, either one, beyond that boundary line, then we know that the machine's not adjusted right. It's giving the wrong mean. They're either too heavy or too light. So at this point, we're going to do the test. So we're going to do a z-test from stats. It gave us a value for mu, which we can pick right off here. Then it asks us for the value of sigma, which we have. And then it asks us for X bar and N, which is about the sample. So X bar is 0.8635. and sample size was 19. And then it's going to ask us about H1, and it's not equal to, and we're going to draw and see what that curve looks like. Now, I made the area in the tails really small because sometimes it is. But that area in the tails is not small. It's huge. So here's a little rule of thumb for you. If you don't see very much black shading when you do that screen, when you get to the draw screen, that means HO's probably not true. Okay? That black is evidence for HO. It's evidence in favor of HO because that black represents a large p-value.
So when you see a lot of black,
HO's probably true.
probably true.
Yeah. And in this case, if you look at the numbers, that's going to bear that out because it says the Z value is 0.54. That's your test statistic. So this is where your sample mean actually fell in relation to what they say the curve should have looked like. Now the reason for the other side is because since we said it could have been less than, it would be just as likely that the sample could have fallen on that side. So there's the other half of your p-value. Remember, I told you this is where alpha lives anyway. P-value comes up when calculator shows you something. So actually, your value of alpha was 0.025 in each side. And obviously, this black area is way bigger than alpha. If you put alpha on that side and alpha on that side together, you still can't even come up to the area that's just on one side, much less two. Yes?
What is the number that you put up on the board and autograph and so same.
Let me make sure I put my numbers in right then. Okay, so stats. 0.85. I got a 6. Oh, I put 6.5. No wonder. That should have been a 3.5. And then 0.0565. 0.8635. Okay, let's draw again and see what happens. Okay, same sort of picture, yeah, but that number change in the thousandths decimal place made a difference. So it's not 0.54, your test statistic is actually 0.7715. But still, you have a lot of black. And the total of that black area on both sides, if I add both of these up together, because it's a two-tailed test, if I add all of that up, your p-value is 0.4404. And when you compare that to your alpha value, there's no getting around the fact that P is larger than alpha. Which means you are not going to reject HO. Remember, the black part is your p-value, and your p-value, if it's a big p-value, it supports HO, it doesn't support H1. Okay? Now, the question is, we do not reject HO. So we've got to think about how we answer this question. This is what we think is true. The evidence supports that. What does that mean about what we should conclude about the claim? Which one was the claim? HO. And the evidence supports HO. Okay?
Say there's sufficient evidence to support that the mean is.
That's right.
If there's a high probability, does that mean it's
Means that that's probably the correct mean. That's probably the correct center. If your p-value is a high probability, that means that it's highly likely that this was true. This as being HO. Now, if the claim had been that it was not equal to, then we don't have evidence to support that. Our evidence supports this. So there's one way to write your conclusion. And at the bottom it says, basically, this is the question we were trying to answer. The green M&Ms appear to have a weight consistent with the package label.
yes?
Yes. Yes, the evidence shows you that they do have a weight consistent with the package label. Because when they put that number on that package, that's what they're saying. When it says when they label that package, that's a claim. When they label your box of cereal as being 14 ounces, that's a claim. That says the weight of the cereal inside that box is supposed to be 14 ounces. When they publish on the can of soda that you get out of the machine that it's 12 ounces. They're claiming that what's inside that can is 12 ounces. Those are all claims. And this is the basis for quality control, because they will randomly select items, particularly at a certain plant. They'll pull some off the line as they go through, and they will check to make sure that those items are being produced consistently. Because how are you going to feel if you buy a bag of M&Ms and your friend buys a bag of M&Ms, and your friend's bag of M&Ms seems, like a pretty normal bag of M&Ms, you open yours up, and you only have about 40 in it, and they had 58. How are you going to feel? Yeah, you're gypped. You paid the same thing they did for a bag of M&Ms, and you didn't get enough M&Ms. Now, you might not go write a letter of complaint to M&Ms, but if that happens to you often enough, are you going to probably buy some other kind of candy? I would. I don't want to pay $1 for a bag of M&Ms and I'm getting, like 3/4 of a bag. And the thing that is believe it or not, the quality control that's the hardest to manage is potato chips. You can check that out with a sample yourself sometime if you wanted to. If you actually weigh a bunch of bags of potato chips, the bags all weigh the same. What's inside of them doesn't, because they package those things, they're supposed to package them by weight. But with potato chip bags, because they have to keep so much air in that bag when they close it up to seal it up, it's really hard to tell the difference because they don't weigh that much. But if you dump them out and look, you can almost see the difference in the bags. Because one will have a lot of chips and the next one might not have nearly as many as the other one did. And that can be within the same, you know, you buy those big boxes of, 24 of them? You can see within one box that there's a lot of variability. So snack companies take a lot of heat for that. Okay. Company drug test success provides a 1-pound THC test for marijuana. Among 300 tested subjects, results from 27 of those subjects were wrong. Use a 0.05 significance level to test the claim that less than 10% of the test results are wrong. Now be aware, this is not part of the problem, but when it says the test results are wrong, those test results can be wrong two different ways. They can show that you used marijuana when in fact you didn't, false positive, or they can show that you didn't use marijuana when in fact you did, and that's a false negative. So there's two ways those can be wrong. Okay? What kind of a test is this? Let's see what information we've been given. Among 300 tested subjects, what is that? That's in sample size. Results from 27 subjects were wrong. Is that a mean? No, that's a way that we can find out the percentage of the tests were wrong. So 27 were wrong tells us X is equal to 27. Okay? Use a 0.05 significance level. As usual, that's alpha. To test the claim nope, just X. Because it didn't say the mean number of subjects. It just said 27 subjects. Okay? Test the claim that less than 10%. So the claim involves a percentage, not a mean. Point 10. What would be true? Oh wait, no, I'm sorry, it says less than. I put the wrong sign. Let me. So there's your claim. What would be true if the claim is not true? Greater than or equal to 10%. So as we've done before, which one is HO? Which one is H1? Okay? Because of that. That means the bottom one's got to be HO then, right? So this is what the picture's going to draw for us. HO says the center of this curve should be 0.10. The claim, because it points to the left, tells us that our p-value and our alpha is going to be in the left tail. So if its alpha is 0.05, this is where alpha lives. Now what our calculator is going to show us is our p-value less than alpha, or is it going to be more than alpha in a larger area? So we're going to go to the calculator and go to stat and go to the test menu. And because this is not a test for a mean, which test do we need? One prop z test.
You said t-test?
There is no one prop t test, there's only a one prop z test. So with that one, fortunately, you only have one choice. You don't have to pick between the two. Okay? So we're going to do a one prop z test. And notice when you do a one prop z-test, anything has proportions, you only get to use data, you don't get to use sample. Or you don't get to use data, you have to use stats. You're not going to have the actual raw data. You have to have the summary. So the first thing it asks you is, what's p sub 0 supposed to be? Well, that's the p-value in HO. What should it be? Yeah, but what's the value, the number? 0.10. And then it asks us, what's X? That's the number of people that actually had false test results. That's going to be 27. And it says, okay, how many people did you sample? Well, that's 300. And then it says the proportion from the sample, which it calls prop. H1 says that that proportion is less than 10%. And then we're going to, like we always do, we're going to draw. Now before I fill in and draw, if we didn't do this test, what proportion of the sample had false results? Let's see, yeah, because 3 goes into 27 9 times and then 300 100 times, so he hacks 0.9. Is 0.9 less than 0.10? Mm-hmm. So couldn't we just come to a conclusion right now? No. The reason we can't come to a conclusion right now is because we do know it's on the left side. Question is it right there? Or right there? Or is it way down here? We don't know. Okay? That's why we do the test. So the reason for that little question was, when you do these things, don't guess. Okay? Don't guess. Because if you'd guessed, you'd have been wrong. The result of the test says that the area in the left tail is 28.19%. And the test statistic is negative 0.5774. So if you compare that p-value to the value of alpha, which was 0.05, what you see is that 0.28 is way bigger than 0.05. So when the p-value is bigger than alpha, you do not reject HO. And then your conclusion would be the sample evidence does not support the claim that less than 10% of the test results are wrong.
Where do we find out? How do we find out how to write this plan?
You think through what you said. This says not to reject HO, right? What did HO say? HO said it's probably more than 10%, at least 10% or maybe more than 10%. But the claim was that it was less than 10%. If this is true, the claim can't be true. So for that reason, since evidence says this is probably true, when we say that the sample evidence doesn't support the claim, because the claim was not HO, the claim was H1. Okay? And what that means to the drug company, drug test success for their 1 pound THC tests, sample evidence doesn't say they're wrong less than 10% of the time. It says they're wrong probably more than 10% of the time. So that means people probably don't want to use that test because that's too high a false positive or false negative result. You want accurate results. If you don't use, it should show you don't use. And if you do, then it should show that you do. You want it to tell the truth. And this test is wrong more than 10% of the time. And since that kind of a test being wrong can create all kinds of problems. It creates a problem if you get tested and you've used marijuana, but it says you don't, because then they're going to send you back out on the job and maybe you're up in that bucket on the electric company's truck working on the wiring, and you relax a little bit at lunchtime and you touch the wrong wire, cut the wrong wire, or just flat fall out of the bucket. That's bad. That's bad for you, actually bad for you more than anybody else, because if you cut the wrong wire and you're up in the working on electrical lines, you're going to die. There's no way around it. You are going to die. Okay? But it's also bad because if somebody that didn't use marijuana, maybe they went in and maybe they have a different metabolism, maybe they ate something that their body metabolized the same way, or maybe their body just, you know, maybe they mixed up the results with somebody else's. That's also possible. And it comes back and says, you are a marijuana smoker, you are fired. Well, that person's out of a job, and they didn't do anything to deserve it. So there's always two ways that the test could be wrong, and both of them have bad results. So you don't want a 10% chance that test comes out wrong. Okay? That's a medical test. That's one of those places where, you know, testing at 5%, they might a lot of times test that at 1%. Because that company's probably going to get sued by a class action lawsuit. Okay. We have any smokers in here? Probably a few, maybe. I'm not going to chase you down and ask you. Simple random sample of 25 filtered 100 millimeter cigarettes is obtained and the tar content is measured. Okay? We've got a value for N. Sample of 25. That's not a very big sample. Tar content of each cigarette is measured. The sample has a mean of 13.2 milligrams. And it has a standard deviation of 3.7 milligrams. Remember, that came from the sample, so that's S. Use a 0.05 level of significance. To test the claim that the mean tar content of those cigarettes is less than 21.2 milligrams. So we have the claim. What is the opposite of the claim? Okay, greater than or equal to. Now, if I were guessing, I would say that this is the claim being made by the cigarette manufacturer. Because too much tar is bad. It's bad for your health. Therefore, should be bad for them. But this is probably a consumer agency that's trying to figure out if they have too much tar. Which of these is HO and which is H1? Okay. And that means HO's got to be the second one. So we'll go ahead and do the t-test. I'm not going to, in the interest of time, I'm not going to keep writing all the test things down, but you should. So this is a, which test? Say again? T-test. And it's a t-test because we have sigma, not, or we have S, not sigma. So we have statistics. The claim is 21.2. The sample mean was 13.2. Sample standard deviation was 3.7. And they only tested 25 cigarettes. So the opposite of the claim was, I'm sorry, H1, not the opposite of the claim. H1 says less than. So that's the right place. And we're going to draw the picture. And this is what we see. Does anybody see any shaded area? Nope. And that's because P is equal to 0. And it should make sense to you that P is equal to 0 because here's where the sample falls. That sample falls almost 11 standard deviations or standard errors from where they said the center was supposed to be. So the p-value is 0. Alpha's 0.05. What do you conclude? Reject HO. If you reject HO, what's true?
Why is it that you reject it?
Because Z is less than, or P is less than alpha. 0 is less than 0.05. The claim is supported by the evidence. The company's claiming that there's less than 21.2 grams of tar in the cigarettes, and in fact, they're telling the truth. They're very strongly telling the truth.
How would you find out if the claims are correct or not?
You either reject HO, which was not the claim, or you don't reject HO, and that means H1 is true, and the rule of thumb is always when P is less than alpha, you reject HO. Okay? Now the question at the bottom of the page says, what do the results suggest about the effectiveness of the filters? Because remember, this was a filtered cigarette. Are the filters effective in filtering out the tar? Yes, very effective. The filters worked. So going back to my original question, if any of you are smokers, you need to be smoking cigarettes that have filters on them if you're going to smoke. Okay?
had been HO, then we would be saying there is not sufficient evidence.
Exactly, exactly. That's why I gave you the two different scenarios where I said, you know, the tobacco company's probably making the one that the mean is less than. But a consumer agency might be making the other claim. The consumer agency would be wrong, but they might be the ones making the other claim. So the claim could be either one. You just have to look at the evidence. Okay, we have one more problem and we're pretty much done. We have some data this time, so we're not going to have a lot that we can actually pull out of the problem. The things that we can pull out is a significance level, and a claim, and the claim is about a mean is greater than 30 years. So from there, we can conclude then that the opposite of the claim is the mean is equal to or less than 30 years, which means this would be H1 because it says less than or greater than, and this would be HO because it has an equal to. So this time we're going to run the test, and we're given only sample information and not sigma, so we're going to use a t-test. But the input isn't going to be from stats. It's going to be from data. And all you have to fill in is the value from the claim, which is 30. And we're going to put the data in list 1. We haven't yet, but we're going to. And then we're going to test H1 being less than. So first thing we need to do is we need to hit stat, go to edit, and enter the data in list 1.
Why are we going with less than?
That's what the claim says. Oh, greater than. I'm sorry. Thank you for saying that, Zach. I'll clean that up. So our data is 32, 33, 32, 23, 33, 27, 33, 45, 41, 52, 29, 29, 38, 25, 32. Check your data, because in this case, if you don't have your data in right, then your whole test is going to be blown. And there's mine. 23, 32, 33, 32. Okay. So back again to the test menu, to the t-test, and make the correction that H1 says greater than, so we should be using greater than in that last line. And then at this point, we should be ready to draw. So y'all go ahead and finish your test. I'll make a note of the values. So when we draw, this is what we're going to see. And I can pretty much tell you right now before it finishes drawing that our evidence supports the claim. I'm sorry. I wrote the claim down wrong again. It does not support the claim. It's supposed to be greater than. So we do have some evidence. We have a p-value. Which is 0.0453. And we have a value for alpha. So which way does the inequality go? Is p less than alpha or greater than alpha? It's less. Not a lot less, but it's still less, and that's all it takes, less. When p is less than alpha, what do we conclude? Reject HO. So evidence supports H1, which is a claim that the mean age of race car drivers is more than 30 years. Now, what we're going to do on Tuesday next week is we're going to talk about Chapter 9 and a little quick review of Chapter 10.
On Tuesday.
Yeah. Monday, I'm sorry. Got my days mixed up again. On Monday, we're gonna talk a little bit more. We're gonna talk about Chapter 9. We're not going back over Chapter 8. I will sometime tonight post the answers to the extra practice that I've got right here, so you'll be able to check your answers. So we'll finish Chapter 9 on Monday, and at this point in time, I am making up an exam for you to take on Wednesday in my math lab. It will be multiple choice and fill in the blank. It will not necessarily be like the homeworks that you've been doing in my math lab. So in order for you to get a chance to go ahead and start studying for it and preparing for it, and this one time, just once, this one time, this is not going to be a comprehensive test. It's only going to cover chapters 7, 8, 9, and a little bit of 10. Pretty much the part of chapter 10 we've already covered. Some basic ideas. And I'm going to make up the practice test for you to go ahead and start practicing so that when you get to the test, the real test will actually be shorter than the practice. But if you do the practice test, you should be very well prepared for the real thing. And there's enough problems on the practice test that are already from chapter 7 and chapter 8 that you should be able to do most of the practice tests now. And then you should be able to finish the few problems I'm going to put on about chapter 9. You should be able to finish those next week. Okay? The practice test, I'm gonna post the answers in Shelby tonight for the practice homeworks. You've also got to practice homework for chapter 8 and 9 together, which will help you review too. And then I'll go ahead and get a practice test put up tonight as well in my math lab. Honey, that was not you. They have been falling apart with red glue. Just lay it up there and I'll tell them we had another little bit of dust.
Is there paper towels?
No, sorry. Gavin, can you catch the projector for me?